Yeah, so hello and welcome students. So we will further study field theory today. So let me start. This is MA415 Algebra course, and this is lecture number 35. Okay, today we will obviously first try to understand the general properties of field extension. So let me start with a field, say K over a field F. So what does that mean? That means K is a extension of field F, and suppose you have some elements, say alpha 1, alpha 2, say let me just choose find an element belongs to K, right? Then we define the new field F of alpha 1, alpha 2. So this is a subfield of K is the smallest. Okay, so when I'm saying smallest, I will tell you smallest subfield of K containing F and this set alpha 1, alpha 2. Okay, so this is the symbol I'm using, and the question is that how do you know this such kind of smallest subfield exists? And this is obviously you can use Jones lemma. So this subfield exists using, obviously you can use Jones lemma, right? For example, just give me idea. So let me just give you ideas. So I hope you can prove it, because I have used this kind of idea several times. So you collect a for example, so let me, your set X is all subfield of K, such that if subset of L, and this set also alpha 1, alpha 2, alpha n subset of L. Okay, so you collect all the subfields containing this and give you the so obviously this is non-empty as K belongs to X. Okay, and then you can use that partial order by inclusion, or rather reverse inclusion of the set of the field. Okay, and then using that you can find out that this X is a poset, and use Jones lemma to conclude this F of alpha 1, alpha 2, alpha n exists. Okay, so smallest subfield containing subfield of K containing alpha 1, alpha 2, alpha n. Okay, and in the case when this is not only true for finitely many element, it can be true for infinitely many element also. You can have such kind of extension which is kind of generated by infinitely many elements over the field. Okay, so the interesting case we are just going to use, so when say n equal to 1, so what does that mean? Suppose you have a field L which is F of some alpha, okay, single element. Okay, then L is the smallest, yeah, so and also if you have L and then K is the smallest subfield of K containing F and alpha. Okay, so this kind of field are called simple extension. Okay, so this L is said to be a simple extension of F. Okay, and obviously these kind of element are called primitive element. Okay, and alpha is called a primitive element. Primitive element element for K or for L. So what is a simple extension? Simple extension is extension of a field F is nothing but an extension field which generated by a single element. You can think like that. Okay, over the field. Okay. So so the natural question which arises, see, this is clear that if alpha is element of F, then L equal to F, right? So if alpha is not an element of F, then L will be bigger than F. So natural question is that we have from F we have find out extension field, right, by quotienting out by minimal polynomials. Is there any relationship between those quotient field and the simple extension or not? Let me answer your question. So answer is yes. So you can have a theorem like this. So what does this theorem tells you? So let F be a field so it can be anything, finite, infinite, doesn't matter, and you have say some irreducible polynomial be an irreducible polynomial over F. Okay, so so what does that mean? That means in never factor over F. Okay, so you already know that. Then you have a field extension in which Px is a root, right? That we proved it already. And so let me write down that is the field. So suppose let K be an extension of F containing a root of, because we know that you have a field containing a root of this polynomial and which contains also F also, that we already proved, root of Px, okay, say alpha, something like that, say alpha is the root of Px, okay. Then you have two things. One thing is that on the one hand you have this field Fx over this minimal polynomial, you just question out by that, it will be a field, you know that. On the other hand you have another field, the simple extension of F, right? So these both are subfield of actually K. So no, sorry, this is a subfield of K, and then you can prove that this is actually isomorphic. Then there is isomorphism between these two fields. Okay, so what does that mean? That means the simple extension which we have described, we just define here, it is actually nothing but the extension coming from this kind of quotienting out by minimal polynomial, which we have discussed, I think, in our one of the previous lectures. Okay, and the proof is also not very technical, so let me just give you idea. So obviously whenever you have a question to something, you can use that for first isomorphism theorem of rings, right? So what is the natural map? So you define natural map, say the homomorphism. So let me define it, say phi x to f of alpha. Okay, and what is the map? So you can understand, so here you have polynomial, you choose any polynomial fx, and then you map into the value of fx at alpha. So let's map it to phi map fx to f of alpha. Okay, this is a natural map, and obviously whenever you have natural map, you can check easily that this is a homomorphism of fields. Because see, so clearly this phi of f equal to f, right? F map to f, because the constant polynomials are always constant under this map, and obviously that means 1 map to 1, other thing, right? So phi of 1 equal to 1, so phi of any constant, c equal to c, right? And not only that, you just use that property homomorphism to choose f1 and f2, and then it will be nothing but f1 f2 of alpha, which is nothing but f1 of alpha plus f2 alpha, which is nothing but phi of f1 plus phi of f2. Similarly, you just find out the product f1 f2. This is also phi of f1 phi of f2. Okay, so this homomorphism you can easily find out. Now once you have homomorphism property, then you can ask what is the kernel of this homomorphism, right? So kernel of this is what? So kernel of this is containing all the polynomial fx belongs to capital Fx, such that f of alpha, see, f of alpha is 0 here, right? So this is 0, right? So what does that mean? F of alpha equal to 0 means what? So this means that so alpha is a root, right? So alpha is a root of this polynomial. So what does that mean? That means f of x such that alpha is a root of fx, right? Now you know that alpha is a root of px, right? And p is the irreducible polynomial. So what does that mean? That means if you take a multiple of, so obviously this contains okay, so both the sides. So this is you can say that this field is containing the ideal generated by px, because whenever alpha is a root of that thing, that polynomial must be inside this px. Okay, and that is you are using just division algorithm, right? Because if you just divide fx by px, you will have px plus rx, right? And you know that rx either r equal to 0 identically, or degree of rx rx less than yeah, so the degree of r is less than 120, so this alpha equal to 0. I don't need this thing, I think. Yeah, so px is sitting inside this, that is obvious, because p alpha equal to 0, so px is sitting inside the kernel. Now we need to find out the any element of kernel is also inside this, so this is inside the kernel. So if alpha equal to 0, so if you multiply g, so this will be fx f of alpha will be q of alpha 187. So okay, so f of alpha will be equal to, yeah, so I think this is you cannot say directly, so I need something called minimal polynomial that I did not use it. So I can say only one thing that is obvious. Okay, so this is, so I can say that I can say that px, this idealicity inside the kernel, that is obvious, as p of alpha equal to 0. Okay, so obviously when you quotient out by something which is inside the kernel, so again you have an induced map, right? So okay, so this is the induced map from fx okay, so what is that? Okay, yeah, so fx mod this, so you will have induced map from here to this f alpha. Okay, so why such a things exist? Because you know that see, if kernel is bigger than that, then you know that this fx mod this kernel of phi, this will be, so you are using Tapas theorem that tells you that fx mod px and then kernel of phi mod px, right? So this is the third isomorphism theorem. You just recall third isomorphism theorem. Okay, so obviously you can always, if you have a map from here to something, then you always have a map from this, from here to that, because this is the this map is the so from here to here you have a natural injection map via this, right? So you can find out a map whatever, so you can say phi dash from this to this is also homomorphism, but here you have a nice thing happening. Why is nice thing happening? Because see, this phi dash from f of x over px to f alpha is not identically 0, right? Identically 0 map, right? Because see, this is phi dash also map say 1 to 1, right? So 1 goes to 1 under phi dash. Okay, so and now you have a field here and you have field here, so any field homomorphism is either 0 map or injective map. Okay, you recall it. So thus phi dash is injective homomorphism, right? Homomorphism. And not only that, you check that this phi dash sends the polynomial x to alpha. Okay, so also I should say also, so what does that mean? That means the image of phi dash. Okay, so thus the image of phi dash is a subfield of fx. Okay, and hence also k containing f and alpha. Okay, so thus image of phi dash is actually equal to f alpha, because f alpha is the smallest field containing f alpha, right? And so you cannot have a subfield, proper subfield of f alpha which is containing both f alpha. So what does that mean? That means f alpha is also surjective. Okay, so thus phi dash is an isomorphism is an isomorphism of the fields. So on the one hand you have f alpha, and on the other hand you have fx over this ideal generated by question out by the minimal ideal generated by this irreducible polynomial. Okay. So the extension what we have discussed earlier, they are actually simple extension that I'm just telling. Okay. So now obviously you can ask a question like what happens if you have, instead of you're taking a root alpha, you're taking another root, say beta, then they are isomorphic as a field, and the answer is yes. Then also they are isomorphic as a field. Okay. In fact, you can prove many like more general result and more generally. Okay, so more generally, if suppose you have a isomorphism from two field f1 to f2, okay, is an isomorphism. Okay, and then one can extend phi as an isomorphism from, so I'm using the same symbol phi from say f1 of x to f2 of x. Okay, I'm using the same symbol. Okay, so if field isomorphic, then the underlying polynomial ring are also isomorphic. How? Because if you choose a polynomial fx, say for example ai x power I equal to 0 to n, and then you map f of f1x to this polynomial summation phi of ai and x power I equal to 0 to n. You know that phi is a map from f1 to f2, so phi of ai is element of f1, phi of ai is element of f2, so this will be an polynomial inside f2 of x. Okay, so you can always, and you can easily prove that this is isomorphism. Okay, so what does that mean? That means this map is sending f1 to f2, and the element you're just x, so everything same, just element you're changing from f1 to f2, right? So this is isomorphism of the polynomial ring. And now if you start with the irreducible polynomial, now if you have say p1x is an irreducible polynomial in say f1x, then obviously you can find out. See, then question is that the question is that can you find out irreducible polynomial under this map? So let's see, can I find out or not. So then obviously this is a maximal ideal in f1x, right? So what does that mean? That means the image of these maximal ideals under phi, that will be some px, right? So this p2 of x is nothing but phi of say p1x, the image under this isomorphism. Then what happened to this? So this is also maximum ideal, right? Because isomorphism keep all the property intact, right? So the maximum ideal will map to maximum ideal. Okay, so this is maximal ideal of f2 of x, right? Okay, so what does that mean? That means so whatever property you are doing for p1, it is also true for p2, right? So thus, with that help of this, so you can easily say that your f1x mod p1x, this is isomorphic to f2 of x mod p2 of x, right? This is isomorphic that you can easily say, right? Now suppose you choose an element a roots of alpha, so now let alpha is a root of p1x, okay, and you choose say another root of p2x, and say beta is a root of p2x. Then what happened? Then we already proved that this extension is simple, right? And we proved that okay, so let me start with f alpha, sorry, f1 alpha. Yes, so f1 alpha is isomorphic to f1x over p1, right? But this is also isomorphic to f2x over p2 of x, but this is isomorphic to p2 of alpha beta, right? So what does that mean? That means, sorry, f2 of beta, that means the field these and these are isomorphic. So this is more general thing. So what does that mean? That means you start with two fields which are isomorphic, and then irreducible polynomial which correspond to each other under the isomorphism. Then if we attach any roots of first polynomial with the first field, and any roots of second polynomial with the second field, then the underlying that simple extension are also isomorphic. Okay, so this is a more general result, so you can easily find out this thing. Now you can maybe I will give some examples. Okay, so let me just start with my AF is say Q in the field rational numbers, okay, and I have a say polynomial, for example, x square minus 2. Okay, now x square minus 2 is irreducible over Q, right? Just use Eisenstein criteria, you can say that 2 divides this, but 2 square 4 does not divide this. Eisenstein criteria tells you that it is irreducible over Z and hence irreducible over Q. That is property coming from Gauss lemma, right? Over Q using Eisenstein STEIN criteria. So Eisenstein criteria gives you this. Then you can talk about what is that field. So the field Qx modulo x square minus 2. This is what? So this will be isomorphic to some simple extension. What is that extension? So this is Q, and then with the root of this polynomial. And you see that in an extension field of this, it has a root which is root 2. So it's actually of this form, Q root 2. Okay. So either you can write down this element of the form A plus B root 2, AB belongs to Q, or you can write down this fx plus ideal generated by this. Now you see that here fx are all linear polynomials, because quadratic polynomials they will be vanishing right here. So we can write down a plus bx plus this kind of, okay. So they are isomorphic as a field. Okay, so these are simple extensions. They are coming from this question with that thing. Okay, so now we have to go to further details to understand about existence of something called algebraic closure, algebraic closed field, those things, and that will gives me. So you remember I am going to prove the converse of the theorem yesterday we discussed, that whenever you have a prime power you have finite field of that order. Okay, so I need the idea of algebraic closure, algebraic closed fields. So let me just define what do you mean by algebraic extension. Definition. So obviously I am just starting with that let k over f should be an extension field. Okay, so an element alpha belongs to k is said to be an algebraic element or an algebraic element, whatever. Algebraic element, an algebraic element over if this alpha is a root of some polynomial. So, or maybe you can say it's non-zero. See, it is zero polynomial, some non-zero non-constant polynomial, I should say. Okay, constant also no problem. Then it will be if some non-zero. Let me write down non-zero polynomial over f. Okay, so if you have some non-zero polynomial such that alpha is a root, then we say that this alpha is an algebraic element, or algebraic over f. Okay, for example, in last example here I have given you see the root 2 is a root of this polynomial over q, right? So root 2 is algebraic over q. Okay, so because this satisfies a non-zero element, a non-zero polynomial, right, over q. So also and so obviously the question is that what about the other element? Like, is all the elements over extension fields are algebraic? So this is not possible. Obviously, I will give an example. So if you don't have thing, so if your this alpha belongs to k is not algebraic over if, then we say alpha is transcendental. Okay, so transcendental element is transcendental whatever over f. Okay, now for example, if I choose my f equal to say what I say, so here let me just do q. Okay, f equal to q, and you choose the natural element phi and I am taking the extension field, say R. Inside R I am taking. Okay. Now you see that I mean, obviously this is not a simple proof. This is a very difficult proof, and I'm not going to give this thing. Pi does not satisfy any such polynomials. So pi is an transcendental and element over Q. Okay, so yeah, so in fact the element of R which are not algebraic is called transcendental number also. Okay, so yes, so this is an example. So now I need to define something. I need to define that whenever it's an algebraic element. Okay, if you have an algebraic element, then there exists a very specific, or there exists a polynomial having very nice property, and this polynomial is called a minimal polynomial. And now let me define it. So the least degree monic polynomial such that, okay, so I am assuming whatever alpha belongs to K over F. Okay, so those I am assuming already. Polynomial such that alpha is a root is called the minimal. So I am saying the minimal polynomial. So this is unique. Okay, minimal polynomial of alpha over F. Okay. So I will write down by the symbol M F alpha of X. So this is alpha and this is over the field F. Okay, this is a symbol. Minimal polynomial of alpha over F. Now note that if you change the field, then minimal polynomial changes. For example, m root 2 q of x is nothing but x square minus 2, but m root 2, and then instead of q, if you choose q root 2, okay, and then this is only linear polynomial x minus root 2. Okay, this is quadratic polynomial, but this is linear polynomial. Okay, so linear polynomial depends on the underlying field also. Okay, now the question is how do you know that if you have an algebraic element, then linear polynomial exists? This is very important question, and the answer we are going to prove it. Okay, so theorem. So let alpha is, alpha belongs to K, is algebraic. So I'm assuming the K is extension field of F. Okay, always algebraic over F, and then this M alpha F X exists always. The minimal polynomial always exists. Okay. Not only that, you can say many things. So you can say that if any polynomial fx, or rather is if and only if fx belongs to capital Fx, has alpha is a root, alpha is a root, This is if and only if both if and only if case this m alpha f divides f. I can say the m of f divides fx if and only in both cases. If m alpha f divides fx, then also f has a root, that is trivial, and the conversely also. So the minimal polynomial of an algebraic element always exists. And how do I prove it? So so let us prove it. So yeah, rather maybe see, least degree manifold I already said it, no? So okay, so we know that okay, so as alpha is algebraic, there exists a polynomial g such that g of alpha equal to 0, right? So without loss of generality, we may assume that gx is monic. Monic means the leading coefficient is 1, monic, or else we will multiply by that inverse of the leading coefficients by the inverse of the leading coefficient to make it monic. Okay, so if it's not monic, then because this is a field, so non-zero element is inverse. Okay, now if you assume, if you just collect S collection of all n such that degree of this gx equal to n and g of alpha equal to 0, so you're collecting all the degree of the polynomial which is satisfied by alpha, right? Then this is a subset of natural number, right? So thus Euler array principle gives you the least degree monic polynomial. Okay, so it gives you the least degree monic polynomial for which the least degree monic polynomial such that alpha is a root. Okay, clear? So this is obvious. So okay, so the question is that or maybe I must I one part. Okay, so I just need one more things here, that mnemonic irreducible, that is missing here. That's what I'm thinking. Irreducible. So let's take the mnemonic irreducible polynomial. Okay, irreducible. Mnemonic, after mnemonic you need irreducible, right? That is important. It's called the minimal polynomial. So here I just showed that you have a least degree mnemonic polynomial. So now I will show that this is irreducible. Now claim this alpha if x is irreducible. This is my claim. So if not, then what happen? So if not, then you can write down, obviously it's reducible, right? So you can write down this is something f1x into f2x, right, with the degree of f1 and f2 both, like degree of f1 and degree of f2. Okay, so let me write down details. So degree of f1 and degree of f2, they strictly less than degree of mf alpha, and they are also still greater than 0, right? And that is the meaning of reducible polynomial, right? But then what happened? Then if you so this is x. If you substitute the alpha, then m alpha f of alpha, this is 0, right? But this is equal to f1 of alpha and f2 of alpha. So you are inside the field and the product of two numbers is 0. So it's only possible, it implies either f1 alpha equal to 0 or f2 alpha equal to 0, right? But this is a contradiction, because this mf alpha is the least degree polynomial such that it has a 0, but you just find out that another polynomial whose degree is less than that, having alpha as a root, that is impossible. So this is a contradiction. So what does that mean? That means mf alpha is irreducible also. So thus m alpha f x is irreducible. Okay, so we just show that this mnemonic polynomial exists, and now I need to show that next, what was the next part? The next part was part 2 was what? So if alpha equal to 0, if and only if m of alpha x divides f, right? So the proof is also simple here. So one part is obvious. So if m alpha f x divides f of not alpha f of x, and then what you can say? Then you can say that fx equal to some gx time m of alpha f of x, right? And hence f of alpha equal to g of alpha times m alpha f of alpha. But this term is 0, so that is 0, because alpha is the root of this mnemonic polynomial, right? So this is 0. Now conversely, suppose if of alpha equal to 0, and I need to find out that the minimal polynomial divides this polynomial, right? So you just you use that equilibrium. Now using Euclidean algorithm, Okay, you have what? So you can write down fx equal to some qx into m alpha of x plus rx, right? With either this identically 0 or degree of r is still less than degree of this m alpha f, right? So this implies, now if you know that f of alpha equals 0, so if you plug f of alpha, that will gives you q alpha mx of alpha is also 0, and so thus you will have r of alpha, right? But r of alpha is degree less than this, so this cannot be 0, right? Unless r of alpha identically 0, right? So what does that mean? So this implies r is identically 0, okay, and this implies f of x is qx times some that minimal polynomial, this is x not alpha, okay. So thus m alpha f of x divides f of x, right? This is the proof. So minimal polynomial always divides any annihilating polynomial. You can think that, like, if any polynomial is 0 on that element, that must be divisible by the minimal polynomial, right? So then what you can say? You can say that so suppose you have so obviously if something is algebraic over a smaller field is also algebraic over it. So now remark, so if alpha is algebraic over f, then alpha is also algebraic over any extension field, right? Field of f, because the polynomial which the minimal polynomial is field polynomial over f is also polynomial over the extension field, right? And so you can talk about the minimal polynomial of f and that field also, right? So what you can say, corollary. So you can find out this nice corollary that suppose so let you have an k over f be an extension of f and alpha is algebraic over k over f, then then obviously alpha is also algebraic over k, so you have two minimal polynomial. Then what is the relationship between these two minimal polynomial? The question is that the answer is that then this m alpha f x is a polynomial inside fx, right? But it is also inside kx also. So this divides m alpha kx, and this division will happen inside the polynomial ring kx, okay. And the proof is not difficult. Now you see that m alpha kx, so m yeah, so I think this is the other way. So this is k, this is f. The field is bigger means the minimal polynomial becomes smaller. So m alpha kx divides m alpha fx, right? So what is the proof? So m alpha f of alpha is 0 in K, and alpha K is the minimal polynomial of alpha over K, right? So by previous theorem, if any polynomial who is satisfied by alpha, that must be divisible by the near polynomial. So this is simple proof. M alpha K divides M alpha of F. Okay, so maybe I will just stop today's lecture by that only definition, or maybe let me just stop it here. Next day I will define. Okay, bye.